Start. Hello everyone. Welcome to today's quantum space time seminar. Today we are very happy to have Shruti Paranjape, who is in University of California, Davis, and she's going to tell us about mass effective operators and locality in the double copy. Over to you, Shruti.
Okay. Thank you so much for the invitation. I'm genuinely so pleased to be back in TIFR, even if it's only virtual. So today I want to talk about this nice set of relations called the double copy relations. And in particular, I would like to generalize the double copy to include external states that have masses and extend the relations to apply to field theories that have effective operators added to them or high dimensional corrections added to them. And the guiding principle throughout all of this will be the locality of the amplitudes in these double copy theories. So the work.
Sorry, your volume again, sorry.
Yeah, I'm very sorry about that. But please keep letting me know if it goes down. Yeah. So as I was saying, it's based on.
Sorry, it went down again.
Okay. Yeah. Is this fine?
Yeah.
Okay. Yeah, I really hope this won't continue to be a problem. Okay. So yeah, it was written in collaboration with these authors over here. So this is Laura Johnson, who's a postdoc at ETH Zurich, Callum Jones, a postdoc at UCLA, Huan Hang Chi, postdoc at Michigan, Henrietta L. Wang, my advisor, also at Michigan, and her graduate student, Aiden Hurdiske, also at Michigan. Great. All right. So let's start. In the talk, I will focus on shell scattering amplitudes. They will all be at tree level, and they will all be in 4 dimensions. When I'm talking adjoint states, typically I will think about
volume, Shruti.
The partial amplitude, which means that I will be thinking about an amplitude with a particular ordering of a color ordering of the external states. I will also try as far as possible not to refer to Lagrangians and stay on shell throughout. Okay. Good. And the reason is because scattering amplitudes can tell us a lot about the structure and the space of quantum field theories. Partial amplitudes, when I talk about them, are nice gauge invariant objects, which are also only kinematical because you've removed any color information. And also on-shell stuff is typically free of ambiguities like field redefinitions, which kind of plague Lagrangian discussions. And finally, tree-level scattering amplitudes, it's very easy to tell whether or not they come from a local unitary theory just based on their pole structure and the residues on those poles. Okay, great. So what is this?
Probably said this, Shruti, but what do you mean by partial amplitudes, please?
Yeah, so I'll have a definition a little bit later. But
Volume.
Yeah, so a partial amplitude basically is where you separate out the trace color part and you're looking at the kinematical structure.
Volume.
Yeah, I'm so sorry. Yeah. So
is it your computer that is automatically adjusting the mic volume?
Yeah, I think every time someone joins the call, that happens.
There should be some setting where you let it not do that, right?
Does somebody here know of how to help her set that setting?
Yeah, that would be great.
Computers?
She has Ubuntu. I don't use it.
No, or is it a Zoom thing? Zoom also has a setting. I don't know.
Maybe give it 5 minutes, and if it keeps happening, I'll try and I'll try and change maybe use a different headphone. Sorry. So I was Yeah, so partial amplitudes, right? So basically what I have in mind is that you have a fixed color ordering for the external states. So you've separated out the color
Volume.
and you separate out the color traces and you only have a kinematical object.
Thank you.
Yeah. Okay. So this structure that I have in mind on the space of theories is the double copy, which basically is a relation that allows you sort of to multiply two different theories A and B and get a third theory C out of it. And these types of relations have, so the original relation was found in string theory. Since then, the field theory limit.
Volume.
The field theory limit has been extended to loop integrands, to classical observables, so like some black hole solutions, and of course tree level amplitudes, which is what we'll be concentrating on in this talk. Okay. So as I said, the original
Volume.
came from string theory.
Sorry, Shruti, can you try this?
Yeah.
There is some suggestion in the chat. If you go to Zoom
Sure.
audio settings, where you see the microphone button, go to the Zoom audio settings, and there is a box which is I guess by default ticked, which says automatically adjust my microphone volume. Just untick that. Maybe that will help.
Okay, I have unticked it now. I'm very sorry about that.
Let's see.
Hopefully this is better.
Sure, it will help, but anyway, it's worth a try. Yeah.
Yeah.
Shruti, could I ask? So these partial amplitudes themselves are not crossing invariant, right? Because crossing will mix up color structures.
That's right.
Okay. And so crossing then is a non-trivial relation between different partial amplitudes.
That's right.
Okay. Thank you.
Yeah. So mostly I won't be using crossing for that exact reason.
Okay. Thank you.
Yeah. Good. Okay. So, all right. So the original example then in field theory was that Yang-Mills squares to gravity. And at 3-point, this is very simple. It just looks like a 3-point amplitude. You square the 3-point amplitude between gluons and you get graviton amplitude. Okay. This was probably a bad choice of helicity states, but please ignore that. Okay. So as I said, this came from a string theory relation, which was first given by Kawai, Lewin, and Tai. So I'll call it the KIT relation going forward. And it expressed closed string scattering amplitudes as a sum of products of open string amplitudes. And the exact formula is given over here. The main thing to notice is that you sum over here over orderings of external states. And you have this object, which is in blue over here, that I'm going to call the KLT kernel. It basically tells you what it means to multiply two amplitudes. And the KLT kernel is given by this nice formula in momentum space to all orders in alpha prime. Good.
What is sigma and gamma in this?
Okay, yeah, good. So sigma and gamma are orderings of your external states. So here, clearly, if this is an endpoint amplitude, there are labels running from 2 through n-2. So it's basically an ordering of those numbers. Yeah, and these orderings are exactly what index this matrix, the kernel, the KLT kernel. Okay. Good. So now if we want to find the field theory limit of this, we just take alpha prime to 0. And obviously you're going to find that the low-lying open string mode looks like a gluon. And then on the other side, you get dilaton gravity. You also get an antisymmetric 2 form. And the benefit of doing this is, well, there are multiple benefits. The most powerful was that it could be extended to loop level at the integrand level. It could also be extended to other observables. And there was this nice property that was found by Byrne, Carrasco, and Johansson called color kinematic duality. Another nice thing in the field theory limit was that we could go beyond this Yang-Mills square example, and we could construct this web of double copies. So this was first given by Cachazo, Hay, and Yuan. And as you can see, this no longer is only gluons. Chi-PT is a model of pions, chiral perturbation theory. And we'll talk much more about this by
question.
Yeah.
So when you say it can be extended to loop level, do you mean arbitrary loop level or low loop level? Because isn't there an obstruction to this sort of chiral splitting at higher loop order?
So when I say loop level, actually, I don't mean at the level of the integral. You can write down a double copy. Yes, exactly.
Yes.
And that, I believe, works to all loop level, but there is then a problem. So I think the state of the art is like 7 loops in n equals 8 supergravity is how far they've actually used the double copy to do a calculation. But at some point, it doesn't become that useful of a tool.
So this doesn't rely on the chiral splitting theory of Doka and Fong?
I don't think so. I think it only relies on the fact that your loop integral on cuts needs to look like lower loop integrals. And then there's some recursive way in which you can show that this has to, this kind of like color kinematic structure has to hold for the integrand.
Okay, because I thought there was a global obstruction when the
they're not doing string theory, Dimitri. They're just doing quantum field theory.
Yeah.
Okay, but KLT came from string theory, right?
The motivation was string theory, but now they've just left string theory behind and they're doing quantum field.
Precisely.
No, but sorry, after Dimitri, I had a quick clarification. Dimitri, go ahead.
Yeah, no, okay, sorry, carry on, Sandeep.
But I was also confused about that little bit, Shruti, that if you are you're leaving behind string theory and you're having this relation between Yang-Mills theory and gravitons, and it's going to extend to higher loops, the graviton correlation functions will presumably be quite badly divergent, right? Just if you don't have all of string theory. Maybe you'll tell us more, but is that supposed to somehow come out in this relation?
So, okay, I will say that I will only be talking about tree level.
Okay.
And the KLT formula itself, there is no notion of it at loop level, but at tree level, there is another formulation of the double copy relations called the BCJ formulation. And that extends to loop level. So, yeah, I don't know if that quite answers your question.
Okay. No, please go.
Also, Sandeep, I think she's going to be talking about the integrand, before the integral of the Feynman variable.
Oh, I see.
So the notion of divergence is also a bit cloudy because you've not actually done an integral, you've not chosen a renormalization scheme, nothing like that.
Oh, I see. I'm sorry. Okay, so just at the integrand level, there'll be some connection, but then presumably once you do the integrals, then you'll see all the divergences of the gravity theory and so on and so forth. Okay.
Yeah.
Go ahead.
So roughly the degree of divergence would be twice as in the single copy.
It really depends because you don't actually square the how do I say this? So you know how in a Feynman integral you have a numerator and then you have a bunch of propagators at the bottom.
Okay.
You don't square the propagators, you only square the numerators. So it doesn't quite scale as a double. Yeah. So and yeah, it doesn't quite scale as double. Okay, great. Okay, good. So as we've already...
Sorry, Shruti, I'm sorry to be so disruptive, but
No,
when you say dilaton gravity, is there no way to just get ordinary gravity without the dilaton?
So the reason that you have a dilaton, unfortunately, I guess, is that in a sense, so what you do, right, is that you have these helicity states in the gluon. And so a plus gluon with a plus gluon will give you a plus graviton. But then if you have a plus gluon and a minus gluon, It has to give you some scalar state on the other side. And so that is basically what becomes the dilaton in the double copy. At tree level, if you're only looking at external graviton states, you can ignore the dilaton and the two form completely. But then at loop level, obviously, you can no longer do that. And so it is genuinely a theory of a dilaton gravity theory.
I see. So you say that at tree level, if you just project onto the traceless part,
yeah,
the external states onto the traceless part, then you really just get the graviton.
Exactly. In a pure gravity theory.
Yeah. Thank you.
Hi.
What kind of interaction do you get for the graviton dilaton? Or maybe you will talk about it.
Not really. I don't think I'll talk about it. So let me say now. So you have usual, like it's like there's a phi H interaction.
Yes, minimal coupling.
Right. Yes.
As opposed to.
Which is why if you're looking at only external gravitons, you can ignore the dilaton at tree level.
There is no coupling to the Riemann tensor.
I think that would be higher derivative.
Yeah.
But there is notion of derivative expansion here, or you will be.
So right now we are at leading order, and sort of our idea was in fact to include effective operators, and once you do, you can have more interesting dilaton gravity couplings.
Okay.
Because you have now high derivative operators that you're allowed to get.
Okay. Thank you.
Yeah. Mm-hmm.
Hi, I have a follow-up to the previous question. Like, so once you write this integrants for the gravity amplitudes, it's just a matter of putting in the propagators and so on, right? So, so can you at least characterize and capture all the possible gravity divergences from this?
So I guess a cavalier answer would be yes, because if you have the integrand, if you can do the integral, then you know what the divergences are. That would be the most cavalier answer. Obviously, this is not an easy thing to do at higher loops. But in principle, the information is there because the integrand is there.
But even like 1, 2, or 3 loops is like for gravity, it's a difference, right?
Right. So I think, as I said, most of the headway people have made is when they have supersymmetry, and then they can restrict to and also in 4 dimensions, because then you have only the box, the triangle, the bubble. I mean, you can do that generalized unitarity type of thing. I mean, that was at one loop, but they have similar master integrals at higher loops, and you can basically write down a basis of what types of things you can get. And yeah, quite a bit of technology goes into those calculations. I agree. It's not at all straightforward. Sorry, I don't know if that answered your question.
Yeah, thank you.
Okay, great. So as I said, there are benefits of taking this field theory limit, but there are 2 important drawbacks, which we kind of already discussed. One is that you are at the leading order, and so you don't have higher derivative stuff. The second is because you've taken alpha prime to 0, you're only left with the massless modes. So you have this strange dichotomy where in string theory, you have infinite corrections, infinite masses. Not that the masses are infinite, but an infinite tower of masses. And on the other side, you have field theory where you have no higher derivative corrections and no masses. So the idea in this talk is going to be to build a bridge between these 2 regimes. So how do you write a more general KLT formula that interpolates between these 2? So basically the question we're asking is, how do you travel in the space of double copy maps? And then once you can do this, what point in that space of double copy maps is the string KLT relation? And why is that point special? We are going to make very little progress on question 3, but we'll make some progress on question 1 and 2. Okay. So yeah, so the first thing we're going to do is develop a formalism to study the space of double copies. In particular, we want to add massive states. We want to add effective operators. Our guiding principle will be locality. We'll understand how the massless limits and leading order limits work. And then, yeah, and always at the back of our mind, the example is Yang-Mills plus mass or Yang-Mills plus other higher derivative corrections. You can think of other examples as well, but in this talk, we'll just think about Yang-Mills squaring to gravity with some decorations on that. Okay, so let's look at this table once again. So I'm going to call this the KLT algebra. It's not an algebra in any mathematical sense, but it's a multiplication table really. And yeah, and one thing to note in this table that's interesting is that this phi cube theory acts like a identity element. So every time you multiply a theory with the phi cube theory, you get the same theory back. So this phi cubed is not regular phi cubed. It is a bi-adjoint scalar with a cubic interaction given over here. When I say bi-adjoint, all I mean is that the scalars in this theory carry two adjoint indices, and they could be in different, like SUN tilde. It doesn't really matter. Okay. Great. So we find that in the vanilla version of the double copy that is already known, this bi-adjoint scalar theory is special and it acts like the identity of the double copy. And this is going to be our starting point from where we generalize the double copy. So our starting assumption is going to be...
Sorry, Shruti, if you can just go back to your previous slide. Will you be explaining this table a little more? Because I didn't understand all the middle entries so well, chiral perturbation theory, how it's connected.
Sure.
And so on. Whenever I'm just, that would be helpful for me.
Sure. So I'm sorry. So the phi cubed, as I said, is the bi-adjoint scalar theory.
Sorry to interrupt, please, but can I just ask you about that? The bi-adjoint indices, are they supposed to be flavor or color? Indices, color indices? Color. Okay, good.
Yeah.
Thank you.
So really you should think of it because, yeah, so for example, if you look at this table and you look at Yang-Mills, so you're multiplying phi cubed with Yang-Mills and it gives you Yang-Mills back.
Okay.
And you can see that in a sense, the KLT formula, it sums over the color information. It kind of removes the color information. So for example, if both of these are only charged under one adjoint group, they only have one color group, then this amplitude on this side has none. That's what happens with Yang-Mills squaring to gravity. Gravity has no color. Which is why when you have an identity element that needs to have an extra gauge index, that then becomes the gauge index of Yang-Mills after Yang-Mills multiplies. Yeah.
Sorry, but in the phi cube theory, there is no gauge field, right?
No. Phi itself is transforms as in the adjoint representation of some group.
Yeah, but then that would make it a flavor index because it's the flavor symmetry of the theory, right? There is no, it's not being gauged.
Right. Within the theory, yes. Within the theory, you are correct that it's basically a flavor index. But once you, so the way it participates in this relation over here is that it will become a gauge index.
Yeah. Okay. Thanks.
Yeah. Sorry. Yes. To begin with, it is definitely just, there is no gauge field or anything. It's just a scalar theory.
And what was that middle column about chiral perturbation theory, so on and so forth? Just to understand.
Right. So chiral, when I say chi-pt over here, I just mean a nonlinear sigma model where you have the usual, basically what you get with the theory of pions is how I think about it. And interestingly enough, chi-pt is also one of the theories that you can double copy. And just like Yang-Mills squares to dilaton gravity, chiral perturbation theory squares to this theory called the special Galilean theory, which it comes up in a variety of places, really. It comes up as the subleading term in the Dirac-Born-Infeld action. It also arises in the decoupling limit of massive gravity theories. Yeah, I think there's some condensed matter interest in it also, but I don't really know about that.
So the fields of chi-pt transform in the adjoint of the gauge group? Thank you.
So there, I guess the indices are just flavor indices, like for pions or something.
Right. And then
you double copy those, is it? You double copy those?
Right.
Okay, go ahead.
Sorry, I was just saying exactly like the color goes away when you square Yang-Mills.
Yeah.
That flavor will go away when you square it to special Galilean.
I see. Okay, thank you so much.
Yeah. So this entry is, I guess, somewhat more familiar. It's Born-Infeld gauge fields, and I guess one thing that is nice to note is how the spins work out. So if you have chi-pt on one side, Yang-Mills on one side, you have to get a spin 1. Whereas if you have spin 1 and spin 1, you have to get at least one spin 2 field. So, and that's again kind of evident just by looking at how the little group will work on this relation over here, which is, with massless fields, very easy to just read off what is happening with the little group.
I see.
Yeah.
So these relations, do they exist in higher dimension or 4 dimension?
So these exist at tree level, these exist in any dimension. They are dimension independent. I don't know about D less than 4 so much, but definitely D greater. I mean, D equals to and greater than 4. It's fine. D equals 3. I think there's some things that become a little more, they change. So I don't want to say anything about D less than 4, but definitely 4 and greater.
Okay. Is there a way to, sorry, this is a bit tangential, but is there a way to square it to get some sort of a antisymmetric 2 form? I mean,
yeah. So when I say dilaton gravity, actually there is a 2 form here as well. So there is an antisymmetric 2 form here.
Right.
It's often ignored in the literature, like very few people will talk about it in their papers, even at loop level, because people have written down some projection operators that if you include in your integrand, it kind of removes the contribution from that 2 form. But yes, it's definitely, it is generated. It basically is, and in 4 dimensions, it's just a scalar, it's some axion field. So it looks like a plus gluon, minus gluon. The anti-symmetric combination of the plus and minus gluon gives you the 2 form, and the symmetric one gives you the dilaton.
Yeah, okay, thanks.
But you can remove it with projections in all loops, is it?
It's definitely true for one loop. I don't know how it works beyond one loop. I can check and tell you, but I don't know off the top of my head.
It's a bit surprising to me somehow. Yeah, no, please go ahead.
Yeah, I mean, it might not work beyond one loop. So maybe, I shouldn't make too strong a comment about that.
Please.
Okay, good. So good. There is a variety of things that participate in such relations, and all of them seem to respect the fact that this biadjoint scalar theory is the identity. So in order to generalize the KLT relations, we are going to use that as the starting point. So the starting point will be any generalization of the KLT double copy has to have an identity element. Okay. So as we sort of discussed a little bit, the KLT formula sort of nullifies color structures, color orderings. And so any identity element will have to be bi-adjoint in order to make sure that when you multiply a theory with the identity, you can get back a theory that has some amount of color structure in it. Another thing that also I quickly went through was the fact that in order for these, the theory A and the theory A on both sides of this equation to have states that transform correctly under the Lorentz group, you need this identity element to be a scalar. Okay, so the way that we are going to look for double copies is we're going to look for identity elements, which is the same as saying we're going to look for bi-adjoint scalar theories. Now, this might seem like a little bit of a jump because it's sort of unclear whether identity elements are enough to tell you everything you need to know about such a relation, such a double copy. So it turns out it actually is, because so if you start with this relation which says 1 equals 1 times 1, you can of course write that in this form over here, and just multiplying inverses on both sides, you can show that the KLT kernel or the double copy kernel is given by the inverse of any full rank submatrix of bi-adjoint scalar amplitudes. In other words, if I write down a bi-adjoint scalar theory, write down the matrix of its amplitudes, calculate the rank, take the inverse, that is going to define what it means, what double copy multiplication means. And of course, not any bi-adjoint scalar theory can do this, because once you have this understanding, plug it back into this with different basis choices, it will be a self-consistency condition on the matrix of amplitudes.
So why can't any choice work?
So one thing is, okay, so if you take this equation and plug it back here, basically,
Yeah,
you're going to have a it will be an equation that only involves M.
yeah.
M, I should say, is the matrix of bi-adjoint scalar amplitudes. So if you choose the bases gamma delta very simply, which is to say that it matches alpha or beta, then you don't get any consistency condition on the matrix. But if you choose a different basis, this becomes a relation between different parts of the matrix to other parts of the matrix.
I didn't quite understand. This is a matrix multiplication, right? Should be independent of the choice of basis. Maybe this is a bit of a kind of a condensed notation, which I don't understand.
Yeah, so it is a bit condensed. So this is not the whole matrix, it is a submatrix. So you've chosen a particular submatrix, and you're saying that for this submatrix, you can say that the kernel for these orderings looks like this. So now the thing is, the rest of the amplitudes in the full matrix need to satisfy the 1 equals 1 times 1 condition using this kernel that I first constructed. Yeah.
I'm sorry, Shruti, you explained this before, but could you say again, M alpha line beta, alpha and beta were particular trace orderings?
Yes, exactly.
And
so they are
M,
a particular ordering of external states.
And M alpha / beta means alpha ordering in the first adjoint and beta ordering in the second adjoint?
Yes, precisely. Sorry, I should have said that.
Not at all. And and why do you say this is a submatrix? Submatrix in what sense?
It's quite literally, so the full matrix will be n minus 1 factorial squared size matrix. But a lot of those entries will be redundant in the sense that the rank of that matrix is actually going to be much smaller. So actually, maybe it would help if I go a little, yeah, okay. So this is the full amplitude, colored rest, and you can break it up at tree level to look like this with the trace structures out. And cyclicity of trace will then tell you that there are only n minus 1 factorial squared independent objects sitting over here, partial amplitudes. This is literally what I'm calling a partial amplitude. But if you calculate the rank of that matrix of amplitudes, it's much lower than n minus 1 factorial squared. So when I say a submatrix, I want to go to reduce the basis size to the point that I only have independent color orderings. So it's a full rank submatrix.
So another way of saying it is that that equation was in some sense highly non-trivial because that the full matrix was not invertible. Right?
Exactly.
So you're doing something in some reduced part and then, yeah, okay, I understand. Thank you.
Yeah, which is why then it is also a self-consistency condition. It's not just matrix multiplication that you do. Okay. Yeah, okay. So now you have the kernel, hopefully, and good. So you have the kernel, you know what it means to multiply. So the next question is, what can you multiply? And that is given by these relations, a equals 1 times a and a equals a times 1. And so that more precisely are these equations over here. And as you can see, they are linear relations among the different orderings in the theory that you are double copying. So Yang-Mills satisfies these relations, for example, so does chi-PD. That's why that table doesn't involve every quantum field theory, because not every quantum field theory's amplitudes will satisfy these linear relations, which are called BCJ relations. So B, C, and J, discover them in a slightly different context, but they're basically the same linear relations between amplitudes. Yeah.
By the way, is the kernel S always invertible?
Yeah, so sort of by construction, your kernel will, okay, so the full kernel won't be, but again, if you go to a appropriately sized submatrix, it will be.
And your consistency conditions is that it doesn't matter which particular sort of submatrix you take.
As long as it's full rank.
Yes, yes. And that's not an obvious thing, and that gives you your consistency. Is this right?
Yes.
Okay, thank you.
Yeah.
Sorry,
exactly.
but what if you have to sum over, you're summing over all these gamma and deltas, right? So one of the entry in the summation may involve computing the inverse, where it does not exist. So I'm a bit confused. In a block that does not have the inverse, I'm a bit confused because the sum seems to be overall gamma delta or not.
So these, so not quite. The gamma, because of exactly the reason that you said, that if you sum over all the orderings, then you're going to come across a point where you don't have an invertible matrix. So you can't do that. So you choose a basis of orderings where M is invertible, meaning it's full rank.
Yeah.
And you only sum over those colors.
I think it's sort of equivalent to putting a projector onto that subspace.
Yeah.
And then which projector you put the answer should not depend on that. That sounds highly non-trivial.
Yeah, exactly.
All right. But then, which projector? No, the projector is the, sorry, I didn't understand, Shiraz. I mean, this is the answer, right? The claim is that you look at the invertible subspace and make the kernel taking the inverse of that.
Yeah.
And now that should hold for all the
now you want to upgrade that to a matrix that's defined on the full space.
Right.
Multiply on both sides by a projector.
Okay.
So S is equal to projector, M inverse projector. Now this is a well-defined object, right? Because where you would have trouble, the projector kills
you. Yes.
Okay. But now it looks like it depends on which space you're projecting onto. And the fact that it doesn't is very high non-trivial. Right? I mean, that's what I'm understanding. Shruti, please correct.
No, I think that is a good way of
sorry, the statement that this condition holds, is it a statement that which subspace you are projecting onto doesn't matter?
Yeah.
Or just
exactly. So it's sort of like basis independence. So as long as you choose a basis in which this matrix is full rank, it shouldn't matter which basis you choose.
Okay.
Yeah, so it's literally basis independence. Yeah,
and then A is this is a statement that A is some sort of it should be some statement about it's the vector space on which this matrix is acting, right? That A is some
Yeah.
null vector or something. I don't know. Can we say it that way?
Yeah, exactly. So that's exactly it actually. So it's not exactly A, but there is a way to formulate this as a null vector. Basically, null vectors of M dotted into A must be 0. If I'm remembering correctly. Yeah, but
Okay.
more precisely, it is this statement. Which is saying, which then again needs to be true no matter what gamma delta basis that you have chosen. To write this formula down.
Yeah, it's sort of like a gauge invariance in this choice. Because the change of basis should be sort of like should not matter. It would not matter if the thing on which you act is gauge invariant under that choice. Which sounds like this null vector. Or not?
Yeah, I don't want to use the word gauge though, because it means so many different things.
I understand. Yes.
Yeah.
Sorry, she said it's not quite the null vector, but the transverse to the null vector. So it should live in the subspace which is not killed, right?
Yeah, I think that's correct, because it shouldn't. You don't want this to be killed because I mean the double copy otherwise will be 0, right?
Yeah.
Right.
Okay. Right, but A should be killed by the null vectors of N, right?
Yeah.
That's perfect. Yeah.
A should be killed by the null vectors of N. Okay. Great. So I hope this was not too confusing. Let me quickly summarize where we are at.
Sorry. Yeah, I understand this only impressionistically. I mean, will this be important in the talk?
This flowchart will be important to the talk.
Okay. Let's go ahead and I will ask question.
Okay, sure. So basically the idea is to look for maps based on what identity element that you construct. So you write down some bijoint scalar theory, either with mass or effective operators, some kind of bijoint scalar theory. Find what the rank of the matrix is. Invert full rank submatrix, get the KLT kernel, solve the BCJ conditions, and then put the solutions to those BCJ conditions together to calculate a double copy. So this flowchart is really what we're going to be doing through the talk. And the underlying reasoning is basically that all you really needed to say was that any KLT double copy has an identity. And obviously the identity would then have to satisfy these relations. Okay, so I think it will help to see an explicit example. So this is the usual double copies identity element. It is a cubic massless bijoint scalar theory. This is the Lagrangian. I've suppressed the indices over here. Good. And you now have these doubly color ordered amplitudes. So you have n-1 factorial square of them naively. Additionally, because the only color structure that enters your Feynman rules or whatever it is you're building, however you are building your amplitudes, the only color structure is the structure constants FABC. So in addition, you satisfy the Kleist-Coif relations. These are relations between these traces if they come from FABC type structure constants. So these give you then n-2 factorial color ordering. Further, if this theory satisfies those self-consistency conditions we were just looking at, so that leads to further redundancies in the color ordering. So actually the rank is finally n-3 factorial. Okay. So at 4 point, this is very simple. So I guess the simplest example would be 3 point, where the amplitudes are either 1 or -1, or G or -G. At 4 point, they look quite simple. The way that you figure out what poles will be present in the amplitude is to see whether the poles are compatible with both the orderings that label the amplitude. So excuse me, in this case.
I'm sorry, Shruti, to slow you down. You went from n-1 to n-2 on the last slide. What
Yeah.
was that, please? How the
So these are called the Kleist-Coif relations. They're basically relations between these trace structures when these trace structures come from a Lagrangian with only FABCs.
I see. Okay.
Yeah.
Yeah. Okay. Thank you. Yeah.
Mm-hmm.
Sorry, but if the matrix is a big enough matrix and this number of particles is small, then there shouldn't be any relation, should there? I thought these relations would come from the matrix relations, when the number of particles will start becoming close to the rank of this matrix, color rank.
Yeah,
or
so
not, that's not.
So, I mean, sort of the first case of interest will be 3-point, where you won't have any relations. And the second will be 4-point, where you'll have one relation, and then. So, I mean.
No, I mean this T matrix, if it is, the you're talking about SU 500, then at n equals 5, 6, I should not see that, right? Or we should not see the relations. Or this is not the matrix relation,
Yeah.
maybe.
Maybe it's the fact that it's made out of commutators. You could also just multiply it, right? In your vertex, you could have taken some matrices and just multiplied them. But the fact that you're doing it out of F, saying you're only taking commutators, and maybe that is the thing that's giving the relation, not quite the matrix.
Yeah, I mean, for example, you could have had something, instead of just the commutators, you could have had a symmetric product of generators, that type of thing over here. And then you won't have these Kleist-Coif relations.
So Abhijit, I think it's a structural thing independent of the size of the matrix.
Oh, no.
Okay, and so this is specifically.
Yeah.
Okay.
So if you have things like this, then you won't have the Kleist-Coif relations.
Sorry, can you give one example of this relation in a simple case?
I can give you the most general form. Just 1 second. Here. So this is these are the relations. I don't know if these are easy to parse. It's
no, just in terms of the structure constants or the adjoint matrices.
I don't think I could give it to you at the top of my head.
Okay, fine. Yeah, fine.
I mean, I can. The paper is by Kleist and Coif, and they show that that these relations are satisfied as long as you have these types of traces.
Hello, can I make a comment? Like for n equal to 4, like this Kleist-Coif relationship, is it like the Jacobi identity of the two Fs? That is what I think, right?
Oh.
Because I think.
Oh, I see. They're coming from there. Okay.
That might be true. I'm not actually sure if they are independent or not. Yeah, sorry, I'm not sure what they look like in terms of FABC or the traces.
Okay, thank you.
Anyway, so okay. Yeah, sorry, I can point you to a reference, but I don't know what they look like off the top of my head. Yeah, okay. So at 4-point, this is the matrix of amplitudes, and as you can see, I have started with the n-2 factorial sized matrix, which is 2 cross 2, and the rank is 1 as expected, which means that my kernel is literally, I just take one of these elements and I invert it, and that gives me the kernel. Okay, So the easiest one to do would be 1 over S. So I can just say that invert this, and then minus S is the 4-point KLT kernel. And now I can impose the BCJ relations. So that looks basically like 1 times the amplitude gives you the amplitude. And as you can see, the amplitude over here is in a different basis than the amplitude over here. I use my kernel minus S. I use my 4-point amplitude given over here. And I put it together and I get a linear relation between 2 different orderings.
So sorry, here I don't understand how you're putting the indices on S matrix. On this S.
Oh, this is the kernel.
Yeah. So why does it have 1, 2, 3, 4, 1, 2, 4, 3 indices?
So that is telling you, wait, what is it?
Just because you inverted that particular element?
Yeah, it's telling you what to multiply, which ordering to match on this side and which ordering to match on this side.
Okay. Okay.
So
that was your arbitrary
because,
choice, right?
Yeah, that was a completely arbitrary choice.
Oh,
I could change this. So if I change this to 1, 2, 3, 4, then this would change to 1, 2, 3, 4, and this would be a completely trivial relation, which will say that A1, 2, 3, 4 equals A1, 2, 3, 4.
Okay.
Yeah.
Is that an example of a projection you were talking about before?
Mm-hmm. Yeah, exactly.
Good.
So like this over here, I've sort of chosen a basis. At 4-point, it's literally 1 ordering, so it doesn't seem like a basis, but I've chosen a basis where it is full rank.
Okay, great, thanks.
Mm-hmm. Okay. Yeah, all right. So this now lets us then write down the double copy. With this minus S kernel, this will be A1234, A1243. And again, you don't have to choose this basis. So if I chose a different basis, like 1, 2, 3, 4 on both sides, then my kernel would look like this, because it would be the inverse of this amplitude. And so it would look slightly different. And these are connected again by the BCJ relations. Okay. Now, one thing that's interesting over here is how locality arises when you do such a map, because basically when you square an amplitude like this, something very bad happens to its pole structure, right? Because you've taken an amplitude which was supposed to only have simple poles at, let's say, S equals 0. And now you've squared it. So now it has a double pole at S. But you know that if M4 belongs to a local theory, it's not allowed to have a double pole at S. So the kernel is conspiring to make sure that you don't get a double pole in S or a double pole in U. At the same time, you know that this on this side, let's say if it was gravity, has to be both symmetric, meaning it must have a pole at T equals 0. But neither of this ordering doesn't have a T pole, cannot have a T pole. So again, the kernel comes to the rescue and provides that T pole for you. So all this basically to say that the kernel is carefully tuned so that your final double copy is a local object. And you can see that naively, if I just messed with this kernel, if I changed it a little bit, I would change the locality structure of the final double copy, which is exactly what I don't want to do. So the question is, how do I mess with this so that the locality is preserved? And so based on empirical evidence that I will keep giving you during the talk, and the fact that we have not seen it violated for any examples that we have checked, we conjectured that as long as you enforce that your matrix of biojoint scalar amplitudes has rank n-3 factorial, your double copy is guaranteed to be local. And the motivation for this comes from the fact that in the massless limit or in the leading order limit, you know that the matrix will have rank n-3 factorial. So all you're saying is that adding these massive deformations or high derivative corrections, you don't want that to change the rank. And as long as you do that, that you do these changes in this way, you will lead to a local double copy. So let's see how this plays out when you add masses.
Sorry, Shruti. Before you add the masses, you maybe I'm misunderstanding, but you started with some matrix of amplitudes for the Bayesian theory that you already knew in the massless limit, right? Where did that come from, please? Was that a particular choice of Lagrangian?
This Lagrangian over here.
Ah, you said that. So I see. And why did you choose this particular? Why not some other Lagrangian?
This is
Oh, because
the
5 cube, you
amplitude.
can. This is the only thing you can do at cubic level. Or no?
This is not the only thing you can do at cubic level, but it is. So amplitudes of this theory match the identity element of the field theory limit of the string theory KLT kernel.
So somehow this is a nice special thing.
Yes, somehow this is bookkeeping in all the right ways. And so we want to preserve this, even though we are going to give it a mass and give it high derivative.
So one way of asking the question you just asked before I rudely interrupted you is to ask what higher derivative corrections to this Lagrangian you can add that preserve the property that you're.
Yeah.
Thank you.
Yes. Yeah. Okay. Right. So we'll start, as I said, by adding mass, and then we'll go on to add high derivative correction. So adding mass, we'll do in a very generic way. So at 4 point, I'm going to just say that the external masses are M1, M2, M3, M4. And each of the channels, I'll allow one massive state to be exchanged. So, yeah. So all I really need to do at the level of kinematics, at the level of amplitudes, is to take my my matrix that I showed you a couple slides ago and do propagator replacements where I make the propagators now massive.
So, sorry, Shruti, just one question. I mean, if your conjecture is that you want it to be of n-3 factorial rank, right, and not less, right? So any generic deformation of this theory, you would do it, right?
It would generically increase the rank.
Okay, you don't want it to be bigger also.
No, I want it to be exactly n-3.
But your explanation of this n-3 rank seemed kind of, this Kleist-Quiff relations and then there is this BCJ relation, right? And that's what makes it into n-3. So if it is bigger than that, then you would say that means that BCJ relation is somehow not satisfied. That's why you conjecture it to have n-3 rank for it to work.
Right. So, roughly that is what you have in mind, that you have n-1 factorial minus n-3 factorial conditions that are being applied to these different color ordered amplitudes, and that somehow is ensuring that your answer is local. And so I don't want to change the number of conditions that are being placed on the amplitude.
So n-1 factorial to n-2 factorial, that would happen, right? Always, because that's a matrix relation.
So that is true if you have those FABC, if that's the only type of color structure. Once we go to higher derivatives, you can have other kinds of color structure.
Yeah, okay.
So yeah. Okay, great. So just to check, I don't have to finish in 1 hour, right? Or like
you know us well enough. You know us well enough to not ask that question.
Okay, all right. Okay, glad to see things don't change that much. Okay, so I just okay. So I have this now massive matrix of massive Bayesian scalar amplitudes, and if for generic masses, the rank is 2, which is too high for me. So I want to reduce it to 1. So I take the determinant, I set it to 0, and placing this so-called minimal rank condition translates to a very nice linear relation between the squares of the masses in my theory. So it places a condition on the spectrum of masses in the theory that I'm double copying. And you can see that once I do this, my BCJ relations clearly have a smooth massless limit, because this, when I take m to 0, both these m's to 0, I'll get T over U, and you might recognize this from a couple of slides ago as the massless BCJ relation. Great. So at 4 point, this is what it looks like. At 5 point, the minimal rank condition just looks like applying this spectral condition to every 4-point subgraph. Similarly, at 6 point, every 4-point subgraph, make sure it satisfies the.
I'm really sorry, Shruti. Could you go back one? You went by the 4-point sort of.
Too quickly.
At least for me. Yeah.
Apologies.
No. So what's confusing me is how did you? I see. The only place the masses entered your A's were in changing the poles. Is this right?
Mm-hmm. Yeah, well, there is also implicitly S plus T plus U equals sum of the masses.
Okay, good. So when you say at 4 point, the rank of the matrix is this, you're assuming that the interaction has not changed?
Yeah, these are the amplitudes. So it's the same type of cubic interaction. It's just that now each leg is allowed to have a particular mass.
Okay, now I understand. But couldn't you have tried to? And you're going to get some conditions on the masses. You're saying, right?
Yes, exactly. Okay. This condition.
It's not possible that you could have played off this, change the masses and also change the interactions a little, so as to make it more general.
Yeah, good. So actually, that is kind of something I've been thinking about now. When we originally did it, it just seemed like too many parameters to play with at the time.
Okay, good. So
but it's a definite extension, and this is not the most general thing. I mean, even the fact that I've only allowed one mass in each channel is not the most general thing, and definitely not what happens in the string kernel.
Oh, I didn't even realize. So you're allowing the okay, yes. So yes. So you're allowing do the external masses play any role in this?
Yeah.
Oh, yes, that's the S plus T plus U constraint.
Yeah.
And then the internal masses deform the poles, and they're allowed to be completely independent.
Yeah.
Okay, thank you. Yes, thank you.
So when you say that all of them are completely independent, that's when you find that the matrix is full rank and that the rank is 2. Yeah, but
Shruti, you here in this, when you do this, you are basically searching in the space of theories, right? Which theories are good. Now, when you write the first interaction, you are assuming that there are 4 types of phi's, one of mass m1, the other is m2, m3, m4. Then you're scattering, let's say what happens when all of different types kind of scatter, right? And this is the condition. But now you could also get similar conditions for different types of scattering in the same theory, right?
Yeah.
For example, 1, 1 goes to 1, 1.
Yeah.
That's a different condition than this.
Yes.
So then if in this family of theories, if you want to find a good theory, you would have to take all those conditions into account and narrow it down, right?
Exactly, which is very non-trivial.
Okay.
And I'll talk about the 2 cases that we know where we can solve them. Yeah. But it's sort of still open. Like you said, it's non-trivial because each amplitude has to satisfy these conditions. So
even at 4 points, even at 4 points.
Even at 4 points.
And then there are additional conditions coming from higher points, right? Presumably, I mean, possibly additional conditions.
Well, actually, that's the nice thing, that beyond 4 point, it's just every 4-point subgraph needs to satisfy the same condition. So at least you're not generating new conditions every time you do this. Okay. Otherwise, I think it wouldn't be sensible, or at least it wouldn't be. It wouldn't be that pretty would be quite an ugly system.
Yeah. Thanks.
Okay.
So would one example of a solution be all external masses equal and all internal masses equal? And there's a 3/4 between them.
Yeah.
And then that will satisfy Abhijit's condition for every order.
Sorry. So,
No,
so
but
you
later
can
you
do
the
that for
internal
that
can also.
particular. Yeah, exactly.
I didn't understand. Please say one of you.
So I think what Abhijit was saying was that you can then scatter the intermediate masses with one another. And so
since
that's why it becomes non-trivial.
I see. Thank you. And since the internal, since your relationship doesn't allow you to set them all equal, since that's the 3/4, then it becomes non-trivial. Okay, yeah. Thank you.
Yeah. Okay. So yeah. So at 5 point, it's the same condition. So I just want to now talk about, because it seems like everything is nice so far, everything is giving you something local, but I want to emphasize why minimal rank was actually important for this to happen. So there's two parts to how locality manifests on tree level amplitudes. One is you have to factorize correctly on simple poles, and the other is you don't have anything except simple poles. So the factorization, actually, you can prove that it'll always work out if you have a massive bijoint cubic scalar theory. The fact that you don't have poles that are, whether or not you have bad poles is a more it's a more difficult condition to look at. So in the case of, so Shiraz already pointed out that this spectral condition can't be satisfied if all your masses are equal, because you have 4m square and minus 3m square, which is not 0. Right. So if you looked at the kernel with all the masses set equal, so you blatantly ignored the minimal rank condition, then you would end up with this mess of a non-physical singularity in your denominator. So this is just to explicitly show you that breaking the minimal rank condition generically leads to non-physical singularities in your kernel. And this is, I guess, sort of intuitive, because you're taking an inverse somewhere of a matrix. And that's never a good idea if you want to preserve pole structure. Mainly because there is a 1/, determinant. So this matrix of cofactors will only have physical poles, because it's just products and sums of things with physical singularities. So the source of any bad pole in your KLT kernel can only come from the numerator of the determinant of this matrix M. And you'll remember that numerator of the determinant is precisely what we set to 0 via the minimal rank condition, which is what gave us the condition on the mass vector. So this is, of course, not a proof that minimal rank always gives you locality, but it is sort of an indicator that minimal rank gives you locality.
So Shruti, in this ansatz, you are assuming somehow only one particle is getting exchanged, right? There could be multiple particles get exchanged. Like one M12 got exchanged only in the 1-2 channel. 1-3 got exchanged in the, but but a priori there could be, it's difficult to tune the coupling so that this guy gets exchanged only in this channel, right?
Yeah.
So that ansatz is not covered. Sorry, your ansatz doesn't cover those theories, right? Or does it also cover? Okay.
No, it doesn't. So you're completely correct that it is not at all an all-encompassing ansatz. And as I said before, so the string theory kernel is in fact explicitly telling you that you can have multiple masses in one channel. So the string kernel looks like 1/sine pi alpha prime s. So you can have s equals minus n over alpha prime. So those are all the masses. And on each channel, you can have those masses. So it's, it's really not an all-encompassing answer.
Okay.
It's sort of a first attempt, I guess, at having a massive double copy relation. So now we look at actually what solves these spectral conditions. And so you have two directions. One is a theory can satisfy the spectral conditions, or particular amplitudes can. So we'll start with the more trivial case, which is particular amplitudes. And you find that Compton scattering will always satisfy these relations. So of course, if you looked at a different amplitude in this theory, it wouldn't satisfy it. So it's just if you're trying to calculate Compton scattering in a gravitational theory, you can do that by studying Compton scattering in a gluonic theory. And here I have some massive scalars, basically. That's what M is, and the gluons, the springy lines, they are massless. Okay, much more non-trivially, if you
sorry,
a KK, yeah.
Sorry, Shruti. Everything you're doing will be tree level, right?
Mm-hmm.
So would one way of satisfying these conditions to be to ensure that there is a consistent truncation to the internal sector? So suppose all interaction, so we've got the external sector and the internal sector, and all interactions are always quadratic or higher in the external sector. Then tree level scattering amplitudes. Oh, no, I said it wrong. No, sorry, please, sorry. I'm saying something wrong. Please ignore. Because you could have mixed amplitudes. I was ignoring mixed amplitudes. Sorry.
Yeah, I think you can always cook up, maybe not always, but you might be able to find special amplitudes that satisfy the relations. But at least we have not been able to find a consistent spectrum that does it, other than Kaluza-Klein, which is what I was going to talk about.
You can do it with all of the internal guys. That would not produce the external guys and poles. But then if you do it with mixed guys, you will. So sorry, I was saying.
Yeah, there's we kind of did these exercises when we were trying to do this as like, oh, maybe actually this works with MA, MB, and then suddenly someone writes down BBBA, and you're like, oh no, well, this doesn't work or something. And so really the only spectrum we know of that does this is the Kaluza-Klein tower.
So, sorry, Shruti, just summarize again. So when you say, just once, when you say only spectrum which satisfies this is Kaluza-Klein, you mean for all the scalars, that's the only spectrum which will meet this condition? Or what did you mean? Just one, sorry.
So so this condition, where is it gone? Yeah, so this condition, if applied to all the masses in a spectrum, in a mass spectrum.
I see.
If you need it to be satisfied by all the masses, any combination of masses in your mass spectrum, the only example we know of is the Kaluza-Klein tower. Otherwise, we know of special cases like the Compton case where it works for particular amplitudes, but of course it won't work for all amplitudes even in this theory.
I see. No, the reason I'm curious is that, for example, there are compactifications in string theory where you have a low-lying spectrum which is different from standard Kaluza-Klein, you know? I mean, for example, non-Freud-Rubin and so on and so forth. And there must be some, when you say Kaluza-Klein, you literally mean Kaluza-Klein, right?
I literally mean S1, so
S1,
that's the mass.
Okay, that's even more restrictive then. I see. You literally mean just S1.
Unfortunately.
But I mean, what about other compactifications in string theory where you take a truncation, just even higher spheres or something?
Yeah, I mean, the short answer is I don't know. I don't think anyone knows. Maybe that's too aggressive a statement. But at least I don't know of any papers that investigate whether or not.
Okay. Thank you.
Yeah, but for the simplest case where you just compactified on an S1 and you have, and I guess, okay, if you have, I assume that if you have any other kind of toroidals or like S1 times S1 type situation, then it would work probably. But the most simple case where it's just S1, your vertices will conserve KK numbers, so your masses will satisfy these linear relations, and then you can just square stuff and show that this relation holds.
Got it. Okay. Yeah. Thank you.
And yeah, no problem. Yeah, so actually, subsequently, there was this paper by Momeni Rumputis and Andrew Tolley, and they basically showed that if you take massive Yang-Mills, a massive Yang-Mills theory in 4 dimensions, and enforce the BCJ relations, then it's actually fixed to be the 5D KK compactification of Yang-Mills. And so this means that you can double copy this, and it will give you some local theory of massive gravity in 4 dimensions.
And sort of KK momentum conservation in this case would ensure that only one momentum runs in the middle of it, any 2 guys scattered.
Yeah, exactly. Which is why it works in this case.
I suspect, higher spaces also, as Sandeep was anticipating, should work, right? Because then there you would have other selection rules coming from, let's say, SU2 or something, and which would make things consistent. Maybe, but maybe it needs to be done.
Yeah. So it's not a priori obvious to me that would happen.
Oh. Okay. So this MYM is what? Massive Yang-Mills, and is defined to be KK compactification, is it? What is the second last sentence mean?
Yeah. So if you take a theory of, so massive Yang-Mills is it almost feels like an oxymoron. They literally take a theory of, so they write down the Yang-Mills Lagrangian and they say plus m square a mu. So you break gauge symmetry. It's and
what does it mean? Is fixed to KK compactification?
Yeah. So then they add some effective operators, and they write down the amplitudes. They enforce the BCJ relations on those amplitudes, and then those fix the parameters of the Lagrangian, and it fixes it precisely to the 5D Yang-Mills theory compactified on a circle. Which means that particular theory of massive Yang-Mills will double copy to a local theory of massive gravity.
I have a question.
Yeah.
So these things also go to a loop order and so on. Is it like, as in these massive theories, like, do you know whether the double copy works at loop order?
No. Okay, so answer in 2 parts. So this, what I just discussed, I have no idea how or whether it extends to loop order, mainly because the KLT formulation has no loop order formulation. So the first thing one would have to do is take this, write it in the BCJ formulation, and then see whether that extends to loop order. That being said, there are some papers where they look at so when you cut a loop integrand, your internal lines start looking, they're off shell, so they start looking like massive lines. And so people have some way of talking about cuts in these double copy loop integrands. I would suggest looking at papers by Johansson and Ochira, because they have some discussion of these types of things.
So do I understand right that like these, when you say double copy has been done to used to go to loop orders, none of these massive examples have been studied to loop orders?
So select massive examples have been studied. So I think they have looked at, so as I said, I think they've looked at massive scalars, minimally coupled to gravity, if I'm not wrong, because they use these to study gravitational scattering and infall and things like that. Somewhat more recent papers.
So, so would also these mass relations then run compatibly and so on? Like the mass relations don't get corrupted? The sum of mass squares.
I guess I don't know. I don't know if, and I don't know how they would be corrected.
I mean, but
in
like
their case,
you would want it to, as it runs, you would want it to like still preserve this doubleability, right?
Right. So you're right. In their case, they're usually looking at a Compton scattering setup. So they don't actually have to bother about they don't care about all the amplitudes in the theory. They only care about Compton, typically. In the other setups that have been studied with massive particles at loop order. But yeah, you're right. You would want this to be satisfied in order for the locality to still work at even just at 3 level.
But that itself, maybe one could like see, right, whether these relations, like say do this run like and preserve the relations, say at both at the angle side and at the right joint side over here.
Yeah, I think that's a very good question.
But wouldn't you expect these to be violated an integrand order and then be restored only an integral order once you integrals generate the mass renormalization?
Yeah, absolutely. Yeah, the way that we figured this out is all at the level of the amplitude. So you'd have to actually perform the integral and choose a scheme and see what is divergent and all of that. You would have to do it properly. You couldn't just do the double copy and write down integrands.
Shruti, one question. So do you have a solution with finite spectrum or just this infinite tower?
No, this is the only mass spectrum that I know of that satisfies.
But could we do something like this, that you take the extra dimension, the 5th dimension, to be a lattice dimension with n lattice points, and then Kaluza-Klein reduce it with n particles in the momentum space. So that Zn charge will then be conserved in the 4-dimensional theory and should give you roughly n particles, right? And then that should also satisfy, I would think. But that's just a thought. Okay. It would be the same kind of mechanism. Yeah.
Yeah, sorry, I'm not familiar with that construction. So what happens to the highest mass in that case? Like,
it would be n, I think. N.
So then
that would be the most wiggly mode on the 5th dimension. But the wiggles, it cannot be, cannot get more and more wiggly because it just n sides, right?
It will go back.
The maximum wiggly it can be is that just n. But yeah, we can talk about it.
Maybe it would work in that case. I mean, because you're right, it will just be linear relations, and then there'll still be the same mass conserving linear relations. So
yeah, Zn has to be conserved.
Yeah. No, that is, yeah, that's an interesting case. I don't see why it shouldn't work actually. So
sorry, but what about this? I thought this theorem said that. What I thought this MRT theorem that you quoted said that this was the unique answer under some assumption.
What is the MRT theorem?
This Momeni-Rombatus-Tolley. This thing that she said that the only completion was Kaluza-Klein.
Well, what is the ansatz? I mean, if you take like a single exchange, then that might be the case.
Right. So in this paper they use the BCJ relations that we list in our paper from this type of setup. So as Yeah, so that's only you're only allowing one mass, intermediate mass. So that might be why they are so restricted.
Okay, thank
you. Okay. So this was going to be my next slide. So maybe if there are any other questions about the massive extension, we can talk about them now. Otherwise, I'll go on to effective field theory. Okay. All right. So let's now do the second type of extension that we were interested in, which is to add effective operators, or basically write down a double copy for effective field theories. Excuse me. Okay. So the way in which we're going to ensure minimal rank in this case is somewhat more intuitive. So you just say that your full biojoint scalar amplitude will be the leading order stuff plus corrections, and you want to make sure that the corrections don't change the rank. Of course, again, they have to satisfy the self copy or the 1 × 1 = 1 self consistency conditions for any choice of n-3 factorial basis. And yeah, when I say that I've added a correction to the usual massless cubic biojoint, what I mean is that when I send the EFT cutoff to infinity, that I get back this thing. So there's always some rescaling you can do of couplings, etc., so that the statement is true. Okay. Okay. So this will be our starting point. As we talked about a little bit before, your subleading corrections to biojoint scalar, they have no reason to look like FABC. You can have more interesting traces of generators that appear in your Lagrangian. So rather than start with a Kleist-Coif independent basis, we will just start with the just n-1 factorial. So up to cyclicity, all the traces possible, all the orderings possible. And then we'll impose again n-3 factorial rank. So for n = 4, this is 6 orderings. So the 6 × 6 matrix will have these 6 independent functions. And of course, there's more to the matrix. There's more over here. But that'll just be relabelings because these are just scalar states. So actually, even between these 6 different orderings, there are relabelings. And so you actually only have 3 independent functions on which you can now place these self-consistency bootstrap conditions. So yeah, so 1 × 1 = 1 again, and you apply that, and you get F6 and F1 in terms of F2. Additionally, F2 has to satisfy this condition, the third condition at the bottom over here. So again, just like with the spectral conditions, the question is not what is the condition, but what actually solves the condition. And we know of one answer that has to solve it, and that is the string theory kernel. So if I took the string theory kernel, I expanded it so that it looked like some low energy effective field theory, then obviously this, if we were doing things correctly, and we are, should satisfy the equation, any of these self-copy condition equations.
So your particles are massless at the moment, right? Scattering particles.
Yes. So when I talk about effective field theories, all of my particles will be massless. Yeah.
And the poles, the exchange particles will also be massless.
Yes, everything. I'm in a fully massless sector.
Okay, thank you.
Yeah. Okay, good. So now it's actually very easy to systematically write down the most general ansatz. And this time, unlike in the massive case, it is the most general ansatz. It's just whatever you can have at 4 point for a scalar amplitude, which is doubly color ordered. And you plug this into your bootstrap or your self-consistency conditions. and you solve, and you find that certain AKRs are allowed, certain AKRs are not allowed. And in particular, you can recover the string theory result by setting certain parameters to 0 and certain others to specific values, basically so that it sums up to 1 over sign. In particular, you'll note that for the string theory amplitude, you'll never have a factor of t. So anything that multiplies t is 0, is set to 0.
Sorry, as a string theory answer, what amplitude are you taking? The dilaton, 4 point. Because sorry, this is the scalar, bi-adjoint scalar as your external guys, right? So what is the right thing to do in string theory?
So in string theory, it's not.
You have to, sorry.
So this, so if you want to think of it as exact in alpha prime, then I don't think there is a local field theory you can write down, which is the analog of bi-adjoint scalar theory. But if you think of it in the small alpha prime expansion, then it's bi-adjoint scalar theory plus some very specific corrections added to bi-adjoint scalar theory, which will then
starting from which, okay, I mean, but what are my scattering states though? Because I don't have bi-adjoint states in my string.
I'm not. So maybe I don't understand.
I mean, 1, 2, 3, 4, etc. These are these M1, 2, 3, 4, etc. These are amplitudes in the bi-adjoint theory, right? Colored with some colors, labels, and so on. So what is it that I'm looking at in string theory to get these expansions, etc.?
Okay. Yeah. So when you're talking about the string kernel, when you're talking about the string kernel, you are no longer thinking of it as coming from a string amplitude. You're thinking of some auxiliary scalar theory, field theory, and saying that, this is just a way in which I can construct the string theory kernel. It doesn't have anything to do with the actual string spectrum.
I see. So from that kernel, I can read off the full matrix also. The full matrix, the 6 by 6 matrix.
Yeah. Okay. From these relations over here.
Sorry, I didn't understand. Just if you go to the next slide, what quantity are you? I'm re-asking, and I didn't understand. The M is equal to something. You've expanded something to get the right hand side. What did you expand to get that right hand side?
The right. Okay. So this is the 4-point string theory kernel.
Where did that?
This one over here. It's where did that come from?
The KLT, right?
Yeah, it's the KLT formula. It's the thing I showed.
This is the same thing that you use for photons to gravitons.
It's this, if that helps. So it's the full. It is the original KLT kernel.
I see. No, but if you could, thank you. If you could go back to your slide.
Sorry.
Not at all.
Yeah.
This M 1 2 3 4 1 2 3 4 or 1 2 4 3. How? I mean, in string theory, how do you know what indices are assigned to this object?
So even in string theory, you have an external ordering that tells you which element of the kernel you're multiplying with which open string amplitude.
I see. So this is just the ordering on the disk.
Yeah.
And
exactly.
And that. Okay. Thank you. I see. Okay.
Yeah.
But manifestly it's solved in string theory, right? Because there is only one function to work with, F2s, comma t. So it's not like there are multiple functions. It's manifestly solved in string theory already.
Yeah.
Because there is a n-3, there is no sixth thing. There's just one thing.
Yeah.
Okay.
It's already solved as it should be. It's kind of a check of our setup. because
Yeah.
if you set up a problem and it isn't solved by the thing that it was inspired by, then you're in
Yeah.
trouble.
Yeah.
Yeah. So it's basically telling you, okay, these self-consistency conditions, they make sense at least in the one known case that we know, that is string theory. Yeah. Right. And then you can do a more general thing, and that general thing, when restricted, again gives you back the string theory answer. Yeah. So again, I just wanted to emphasize that had we not imposed minimal rank, bad things would have happened. So if I had added just some quartic deformation to the bijoint theory, and I've chosen this one over here, and I've chosen this one because it's very simple. DABCD is a symmetric, is symmetric in ABCD. So all the amplitudes, all the orderings will just get a plus lambda in the amplitude. Lambda is the quartic coupling. And then the rank of my matrix is 2. And you can see that the determinant, the numerator of the determinant now has this s plus 2t whole square, which is telling you that there is a bad pole at s equals minus 2t that shouldn't exist. So, or to say that, again, even in the case of effective operators, ignoring the minimal rank leads to spurious singularity.
So, sorry, Shruti, if you count the number of suppose we impose no condition, we count the number of coefficients as a function of unknown numbers as a function of derivative order. That would grow with derivative order. Right? And now, after you impose your condition, the number of unknowns still grows with derivative order. I mean, there's an yeah. First, there's an infinite number of theories you single out this way, right?
Yeah. Yeah. No, it still grows. As far as we can see, it still grows with derivative order. It grows much less fast than the number of available things, but it still grows.
Okay. So it's a large infinity of large infinity of theories. Okay, thank you.
Yeah, I guess it's a slightly smaller infinity of theories because you placed a constraint on it, but it's still infinite.
Okay, thank you.
And the effective action for the scalar that you would write down this way from string theory, that's some, does this have any physical meaning, or it's a really auxiliary object?
No,
because it's coming from string theory, right? Somehow.
Yeah, I don't think it has any physical meaning. I mean, actually, bijoint scalar, even the field theory guy is not that sensible, right? Because it's a cubic theory.
Okay.
You can only take it seriously so much. You can't take it too seriously. Yeah. So yeah.
Okay.
Yeah, that's all I think I can say. Yeah. And with this, in the string theory case also, you have these negative mass square poles. So yeah, really, I don't think you can think of it as a physical quantum field, as coming from a physical quantum field. Yeah, in the low alpha prime limit you can, which is what we're doing. Yeah. Okay. Okay. So good. So now we have this bijoint Lagrangian. This is the corrected Lagrangian. There are more corrections after this, but I have spared all of you the gory details. And now that we have this, we can search for things that satisfy the BCG relations to see what it is we can actually add to Yang.
Sorry, and this here you've truncated to two derivative order in interactions, right? Is this right?
Yeah.
And the number of couplings before you did your truncation, so you've got now 3 couplings after your truncation? 3
2.
plus at 2 derivative order?
2 couplings.
2. Oh, I see. 2 couplings. Okay. And the number of couplings before you did your truncation would have been 3? Before you did imposed your conditions, or more?
So I think it would have been more, because you would also have things. So this is F, D, and DF. but you could also have DD. So like here, I mean, dressed with derivatives, but this term, I think you could have something like this, and this would be set to 0 as well. Yeah, yeah, the space is quite big before you impose the conditions.
Okay, thank you.
Yeah.
And you can't add higher derivative terms at the cubic order because you can field redefine those away.
Yeah, exactly.
Okay.
Yeah, which is where it really helps to be massless. Yeah. Okay, great. So, all right. So what can we double copy with this? So at 3 point, the VCG relations are very simple. All they tell us is that identical states, amplitudes have to be antisymmetric when identical states are exchanged. This is obviously satisfied by Yang-Mills. In addition, it's also satisfied by the F cubed interaction, which is higher derivative than the Yang-Mills interaction. So these are our only possibilities. These are our only spin 1 possibilities at 3 point. We can now use that as input to construct the pole terms at 4 point. And in addition, you add an ansatz for all the contact contributions. And I've only shown the MHV sector over here. In principle, because you have an F cubed interaction, you will also generate all plus and all minus, and all 3 pluses, 1 minus, all of those combinations. Okay, so then you impose the BCG relations and you get a final answer. And one thing to note is that all of these H coefficients get fixed in terms of the E coefficients. Another thing to note is that genuinely you are allowed to now double copy more things because you looked at a more general kernel. So the A coefficients, to remind you, are what the corrections to the kernel. So had this been 0, you would not have had a term that looked like this. All right. So now we can use this Yang-Mills to
So that was an most general ansatz for the Yang-Mills amplitude?
Yeah, at 4 point, yeah.
Yes.
And then you can double copy that to get the gravity EFT. And here something strange happens, which we don't quite have an explanation for, which is that all the freedom that you had in Yang-Mills is actually, it just kind of disappears. So you can see that over here. You can see that I can absorb these kernel corrections into the couplings of Yang-Mills. I can do like some kind of shifting around, redefinition of the couplings that absorbs this into that. So you end up generating the same operators in the double copy, even though a larger class of models can go into the double copy. So a summary of our results at 4 point, and the 5 point ones are quite similar, are given over here. So this tells you the total number before any constraints are placed. This tells you with the regular cubic bar joint, with the string kernel, and then with the most general kernel. And these are the numbers. And you can see that in the case of gravity, that all of these numbers are the same. And we don't know why. Yeah.
Sorry, what is the string? What is the string 112 there? I thought the string theory just fixed, right? The 0, 0, 0, shouldn't be?
Yeah, so these are the number of independent operators that are produced. So they'll be independent because you'll be allowed to add these contact contributions to Yang-Mills.
No, but in string theory, that should just be fixed, right? In string theory, there's no operator you can add,
okay.
right?
Yeah, sorry. So I should explain a little better. So when I say string theory, I've taken this, but I've given them free coefficients. So it's like A1 over pi alpha prime S, A2 S. Yeah. So basically to see, what kinds of operators are generated in all of these cases. Yeah. Okay, so really the last kind of topic I wanted to touch upon
Sorry, when you
is
say total, you mean without just the ansatz without any possible restrictions?
that's right. Yeah, I mean Bose symmetry, if
Yes.
if applicable. But yeah, that's it.
Right.
Oh,
What is
also
the
on
last
shell.
column? What is the last column? Cubic
This one?
biadjoint.
Yeah, so that is the uncorrected. So if you just have the leading order cubic biadjoint.
But that was also fixed theory.
Yeah.
So the stuff that follows from it should also be fixed, right? So I don't understand 1, 1, 2 also again.
So in that case, actually, a lot of these coefficients remain unfixed. They will just satisfy the BCJ relations.
Mhm.
Yeah, without their values being fixed. Yeah. So
even though the cubic theory that you started with, the adjoint biadjoint scalar field theory, the one of your algebra was some fixed one. Even then, there is a freedom in solution.
That's right. Yeah.
Okay.
Yeah. Is that because basically the constraints come from the exchange part, but not from the contact parts?
Yeah, mostly because yeah, that's usually the case.
Yeah.
But there are still restrictions, of course, even on the contact contribution.
Because you can square a contact with an exchange because there's a cross term kind of, right?
Yeah, I mean, you cancel some of this with that, and there's some,
okay, and sorry, I didn't. Could you go back to your table? What about trace f squared, trace f squared?
Oh, so this is schematic. I mean, when I say trace d square f4, there are all kinds of combinations. Is that what you mean?
Suppose we go to the first line, where you've said there's only one structure.
Yeah.
I would have thought there were two, because there was trace f to the 4 and trace f square, trace f square.
I think trace f square is up to equations of motion the same as trace f to the 4 in the MHV sector.
Oh, because this is for them. I see.
Yeah.
I see. Okay, thank you.
Yeah. Okay, great. So the last sort of topic that I wanted to talk about is what happens actually when you stray away from minimal rank and you deal, and so basically, can you deal with the spurious points?
Sorry, maybe we can ask this in the discussion section, but I wanted to understand what your interpretation of these results are. So you say that in gravity, you're getting no, the counting for the total number and the counting for the, after you impose your constraints, is the same, right?
So this is actually not a generic feature, the fact that total equals generalized. But the fact, I mean, generic in the sense that if I look at a different helicity sector, or if I look at 5-point, this changes the equality of these two columns. But the equality of these two columns is really, that seems robust, at least in the examples we've checked.
I see. If for 4-point scattering, is the total and generalized always equal?
I have to check our results in the other two helicity sectors. My guess is no.
I see.
Yeah.
I see. So, okay. So let's say the answer is no. So you would say that in the space of all possible gravitational scattering amplitudes, there are some that can be built out of the square of Yang-Mill amplitudes and some that cannot. Is that an accurate summary?
Yes.
Okay.
Yeah.
Thank you.
Yeah.
Sorry, but I don't understand. Sorry, I mean, if you give the algebra element 1 is fixed, I thought the way you are constructing these theories. Oh, I see. You the way you would write Yang-Mills, generalized Yang-Mills, is by that relation there, that null vector kind of a relation there. And then that you are saying has some space of solutions.
Yeah.
I see. Similarly for gravity.
Yeah. So you have some free coefficients. So like these green coefficients are the free ones that you inherited from the Yang-Mills.
Yeah. Thanks.
Yeah. Oh, by the way, so you were asking about the dilaton, etc. So you actually do have over here, you have exchange channels, not just of gravitons, but you also have to, you also exchange other stuff because you have high derivative contributions.
Thank you.
Okay. Okay. So yeah. So what happens with non-minimal rank? So as I said, when you have non-minimal rank, generically you develop spurious poles in your kernel. And so, sorry, I'll have to scroll back a little bit. So you remember that at 5 point, I developed this very bad looking non-physical singularity. But there's actually something special about this particular polynomial. It is proportional to the 4D gram determinant. So actually, sorry, yeah. So in D equals 3, that vanishes. And so the rank reduces a little bit. It still is it's still non-minimal. So there's still spurious singularities, but miraculously, topologically massive Yang mills in 3D, its amplitudes exactly cancel out any spurious singularities. Which is to say that in 3 dimensions, topologically massive Yang mills satisfies the massive BCJ relations and double copies to topologically massive gravity. And this is without any Kaluza-Klein tower of states or anything like that. It's just a single mass vector. And so what I've talked about in the talk so far is that when you have minimal rank, you have locality. This is kind of the converse, or this is telling you that the converse isn't true. You can have locality even if you don't have minimal rank, but it's not a generic feature. It's something special. Careful cancellations have to happen for it to take place. This is work by Nathan Moynihan, Mariana Gonzalez, Bomeni, and Rumbutis.
So topologically massive Yang mills means Yang mills with a Chern-Simons term?
Yeah, so it gets, yeah.
Okay, thank
in
you.
3 dimensions. Yeah.
Yes.
Good. And also a non-minimal example with effective operators. So rather than starting with biojoint, this like FABC biojoint, I could do something more drastic and start with one of these interactions. This is a different type of cubic interaction. Or I could not use cubic interactions at all and start with quartic interactions. And in both cases, the rank is not n-3 factorial, so it's non-minimal rank. And in both cases, I will generate spurious singularities. In the first case, I generate them at 5 point, and in the second, I generate them at 8 point. Nonetheless, there are special theories that will cancel these spurious singularities. And in these 2 cases, they are just the single color scalar theories. So basically, if I took this and double copied it with itself using this kernel, I get phi cubed. If I use this with this kernel, then I get phi to the 4th. So these are somewhat trivial examples, but they are basically telling you that the converse of the minimal rank condition is not true. So minimal rank implies locality, but you can have things that are local even if your kernel is not a minimal rank kernel, as long as you have these cancellations of these bad poles that occur. Great. So I think we talked about a lot of these open questions already. The multiple masses we talked about a little bit. There's also a question of other states. So we only talked about adjoint states, but people have studied fundamental matter couplings as well. So, and there I think there's the rank is no longer n-3 factorial. There's some, they have a different rank formula. So it would, the structure would be similar, but still would be, I think, significantly different. Yeah, there's of course also the question of landscape exploration. That in some cases we did a general study, but in others, like in the massive case especially, we did not. So what satisfies the spectral conditions, and how many theories are out there that you could apply this kind of map to. Finally, something that I'm currently thinking about is massive supersymmetric theories. So in the case of the massless double copy, supersymmetry actually commutes with a double copy. So like n equals 2 Yang-Mills, double copied with Yang-Mills gives you n equals to 2 supergravity, n equals 4 gives you n equals 4, n equals 2 times n equals 2 gives you n equals 4. So yeah, and these are non-trivial when you think about the fact that there's some, I mean, the R symmetry groups also have to work out correctly. So it's quite non-trivial. So yeah, so then the question is, how does this work once you have supersymmetry in the massive case? So a lot is, so very recently actually, people figured out how to write massive on-shell supersymmetry. So using those techniques, figuring out what kinds of amplitudes you can even have, and then whether they double copy is something I'm thinking about now. Yeah, so that's kind of all I wanted to say. This is my summary slide. Yeah, so we looked at local extensions of the double copy. We did that by looking at deformations of biojoint scalar theory. And the guiding principle was the minimal rank condition. The minimal rank condition for massive deformations looked like a condition on the mass spectrum, which was satisfied by Compton amplitudes, and it was satisfied by Kaluza-Klein, S1 Kaluza-Klein towers. In the case of effective field theories, the minimal rank condition looked like some self-consistency equation that the amplitudes had to satisfy. And then we could write down explicit PCJ compatible corrections to Yang-Mills. Yeah, so thanks for inviting me, and I'm happy to take more questions.
Okay, thank you very much, Shruti, for a very nice talk. Let's all applaud.
Thank you.
Okay, so we have had many questions, and Shruti has answered very patiently, but if there are more questions.
I wanted to ask a sort of general question, and you find that there are some theories that can be sort of whose double copies make sense, and some theories that don't. And relatedly, some theories can be thought of as square rooted from a double copy, as the square of a double copy, whereas some cannot. Mm-hmm. Does anything else nice happen with those theories that do obey the double copy relationship? Is there some other indication independent of double copy that tells that these theories are somehow special? So it's a vague question, I'm sorry, but.
So maybe one answer, it's a bit orthogonal, so you may not consider that very special, I'm not sure, but let me just point it out anyway, is soft behavior of these particles, behavior in the soft limit. So Yang-Mills in the soft limit goes as, so let's say you have some soft parameter epsilon, it will go as 1 over epsilon. Chi-PT, chiral perturbation theory, goes as epsilon. Phi cubed also goes as 1 over epsilon. Okay. Yeah, I think that's correct. Yeah. So the KLT kernel itself goes as epsilon. So one nice thing about this table is that the soft behaviors actually work out really nicely. So if you have, so chiral perturbation theory goes as epsilon, chiral perturbation theory goes as epsilon. So together they give you epsilon squared, and then the KLT kernel gives you another epsilon. And actually, special Galilean theory has enhanced epsilon cubed soft behavior. Similarly, of course, Yang-Mills times Yang-Mills will give you the appropriate soft behavior for gravity. Again, with Born-Infeld, I think goes as epsilon to the 0, which is what you'll get when you look at Kaipiti and Yang-Mills. Sorry, I think I said something wrong. Yang-Mills goes as 1 over epsilon squared. Yeah. Of course, okay, this really depends on how you're defining epsilon, but there is a consistent way of doing this. And you can see very nicely that all of these have well-defined soft limits, or rather they have soft limits that characterize them as theories. Yeah, so in that sense, they are special.
The higher derivative corrections, do they change the soft behavior? Because I thought they would be subleading, right, in low energy.
Yeah, so in the case of, yeah, no, you're right. So in the case of Yang-Mills and gravity, in the case of anything with 3-point interactions, the soft behavior is pretty much determined by the 3-point interactions. So, so you don't have a problem there. In the case of these like nonlinear sigma models, special Galilean, etc., you're kind of it's not guaranteed that higher derivative corrections will preserve soft limits, but it's kind of, how do I say it? You always have enough derivatives to ensure that you're soft enough.
Yeah.
Yeah.
Right.
Sorry. So you said that this table, the squaring commutes with soft behavior roughly, if I got it right. Yeah. But suppose I was just interested in the gravity theory itself, and I wanted to know that some Lagrangians are, or the Yang-Mills theory itself, and some Lagrangians can be obtained from a double copy, and some can't. Now I forget about the double copy completely. I just take the gravity Lagrangians themselves, and I want to see some other way in which the guys who can be squared are special. Something else that makes no reference to double copy at all.
Right.
Is there something to say or not known?
I guess I can't think of. Yeah, I mean, everything I think of kind of somehow relates to the double copy. Like the fact that you have this CHY formula for gravity, where you can write the amplitudes as an integral over punctures on the sphere.
Okay, so you say that suppose we take your higher derivative corrected gravity theories, they would admit the string theory like amplitudes.
Yeah, so that's the hope. That's not something anyone has worked out yet, but that is the hope. Actually, it's not even been worked out for any kind of higher derivative corrections to gravity. The CHY formula, as far as I understand.
Okay.
Yeah. So, but in terms of the leading order, that is something. I guess that's one special thing. But yeah, other than that, I don't know. I mean, what would be nice is if, for example, if you had a theory of Yang-Mills that lay in this, I don't know. So Nima has this EFT hedron that he been talking about. Basically, it's EFTs that are UV completable. So let's say you took a theory of Yang-Mills whose corrections lay in this EFT hedron. Would that guarantee gravity corrections that lay in the EFT hedron? I think that's an interesting question that someone should investigate. Maybe me.
But this EFT hedron will put constraints on the magnitudes of coefficients, right? Right. What you have, there's nothing like that, right?
Yeah, but I imagine it could also say that such a coefficient can't exist.
I see. Some zeros you could get, but not the bounds. Yeah.
Yeah, no bounds. No bounds. Yeah. But yeah, sorry. Otherwise, I don't know how to motivate.
Okay. Thank you so much.
Actually, if you I have a small question as well. If you have a generic double copy relation, C equals A times B, and you introduce a ghost in B, let's say, would that show up as a ghost in C, or would that show up as some other inconsistency?
So what do you mean by ghost, are you thinking of like an off-shell ghost, right? I mean, there's no such thing as an on-shell ghost.
I'm not sure what I mean actually.
I guess what I'm saying is that
on-shell,
you could
off-shell?
never have, I mean, ghosts don't show up as on-shell external.
Ghosts that show up, if you put one in the external state, that it will show up in loops as well.
Right. So yeah, exactly. So right, good. So it would show up in loops.
Let's say in theory B. And then what happens in theory C?
Yeah. Yeah, so I think, yeah, okay, good. Okay, so if where are we? Yeah. So, yeah, okay. So the way that it works at loop level is that you write your integrand. Let's take the example of Yang-Mills, right? So you write the integrand as some color factors times numerators over the Feynman propagators, and you sum over them. And then your gravity integrand is given by replacing the color factors by whatever was multiplying them in the Yang-Mills case. So you don't actually have to put in the fact that you have ghosts, because if they were already present in the original Yang-Mills amplitude, if that makes sense.
Yeah.
Yeah.
Yes. So actually, yeah, what I actually meant was if you replace theory B by a new theory that has ghosts, that's what I. When I said if you include ghosts in theory B, what I meant was if you replace theory B with a theory that has ghosts. If it will show up as ghosts in the theory C, or if something else will, if there'll be some other inconsistency instead. Or maybe there's the whole, I mean, there will just be no double copy in that case, or I don't know.
Yeah, I'm sorry, I'm just I'm not entirely sure how to answer your question. Yeah, so the way that you normally go about it is you would use these like unitarity cuts to say what kinds of what kinds of loop integrands you would have, and then you would replace the color factors by the numerators. And I'm just wondering, when you do that, how do I say, when you do that rewriting, whether you are sensitive to the fact that there are ghosts in the theory or not. And I'm
Dimitri, can I think of this as just the let's say a tree amplitude in the theory with the ghost as a pole with a negative residue?
Yeah.
Yeah, and now so let's say 1 over s that Shruti was talking about gets replaced by, let's say, something like a minus 1 over s, right? And then the question is whether if you use that theory to make a double copy, would the resulting theory would it have a negative north state, which would be seen as a again negative residue of the double copied theory, right?
Oh, I see.
Is that
Okay.
one way of asking your question?
Yeah, that's the kind of.
Oh, I see. Okay, I think I was answering a very orthogonal question. In that case, yeah, I think they would show up in the theory C.
As ghosts in the C. Okay.
Yeah, yeah.
In the cross terms, right? The square will not, but yeah.
Yeah. In the cross terms.
Anyway, just a curiosity, really. I don't know.
Yeah, sorry. I think I was answering a very perpendicular question.
Any more questions? I think it must be very late, and we should thank Shruti for a wonderful talk again.
Thank you.
Shruti, that was amazingly clear. Thank you so very much.
Oh, thank you so much. I'm so happy to be able to do this.
Thank you. Thank you.
Okay.
Bye.
Bye-bye.
Bye.